I also need a candidate to solve it on the board. Anyone who wants to solve it using induction, preferably. Anyone? Please. Everyone else, listen carefully. And, biraz anlatsan iyi olur. Yani yazarken söylersin ne yaptığını. Okay, listen carefully. It's important to follow up. So so it's trivially true for n equals 1. Both sides becomes equal. Maybe you need to say it differently, but it's true for n, then it's true for n plus 1. That's what you need.
I'm using binomial.
But if you used binomial, then you wouldn't need induction, right? I think you need to separate 1 plus x to n plus 1 into 1 plus xn and times 1 plus x. And if you use binomial, then you will have to prove that too. Or that also comes from induction. So, you want to try with n plus 1 or? Yes. You need to write the 1 plus x n plus 1 as 1 plus x n times 1 plus x, and then use this and work with inequalities. Or you can try that. See, binomial theorem is a theorem that you also prove using induction. There are other proofs too, but this is the... So then you have to verify that the right-hand side is bigger than 1 plus n plus 1x. So. Okay, that's sorry? Huh?
Yok, en yerine n artı 1 yazmadım. Her iki tarafı da 1 artı x ile çarptım. Bir... Ha, evet.
En yerine n artı 1 yazdım.
Hayır. Ya bu n için doğruysa n artı 1 için de doğrudur diye bakıyorum ama en yerine n artı 1 yazarak yapmıyorum bunu. 1 artı x ile çarparak yapıyorum.
She used multiplication with 1 plus x. But for that, this is actually a good point. So you have 1 plus x to the n, you say this implies 1 plus nx, gives you this, right? So you multiply with 1 plus x. So under which condition the inequality will stay? Same?
When x
You need this to be
minus 1.
positive.
Yes.
So you need x bigger than minus 1. Do we have that?
Yes.
Yeah. So we can do this because x is bigger than minus 1. Let's finish. And now use x squared is bigger than 1.
Yes.
And then gives you, so actually you need x squared bigger than 0. So you need, what you need to prove is 1 plus n plus 1x. So this part. So you just need to say this is bigger than 0.
Yani onun sıfırdan büyük olduğunu söylemem yeterli mi?
Sadece şuraya ihtiyacım var. Şu kısma ihtiyacım.
Yani ne yapmam için anlamadım.
Şimdi göstermek istediğin şey şu. Şu. Buradan buraya geçmek istiyorsun. Dolayısıyla şundan kurtulmak istiyorsun. Onu da şöyle kurtarabilirsin. Tamam? So this arithmetic step is that when you multiply these two, you get 1 plus x plus n plus x squared, and you need this one. So you just need x squared be positive. And that's always positive. So this arithmetic step is also true. Okay, so setting up is x equals 1 is true. You assume for n equals arbitrary n is true. You want to pass to the n plus 1. You multiply both sides with 1 plus x. To keep the inequality in the same direction, you just need this to be positive, which means you need x strictly bigger than minus 1. That's where you need this. So if you haven't used that, you probably made something wrong. You need to use this somewhere in the thing. So,
instead of n, we can use n plus 1 and then
go from there with expanding. It's probably better writing actually, to start with 1 plus x n plus 1 and then simplify from there. But I see many of you solved it. So, but using things like this, like binomial expansion, you use something that is also proved by induction, and we haven't done it in this class yet. So that is not, at this point, it's not acceptable to use formulas that we haven't done yet. Okay. Any questions on this before we move on? Okay. The other thing we did last time was this greatest common divisors. So let me continue on this. So remember we had this calculation on the board last time. And then we did this calculation. Okay, so I will repeat what the greatest common divisor was for two integers, but what we learned last time was called Euclid algorithm. for finding greatest common divisors. And it worked like this. If you are given two numbers, positive integers, you divide the big one to the small one, you find the remainder, you find quotient, and then you carry this to the next, and then you carry the remainder here, you make another division. After the second division, you get another quotient and remainder, and you carry this again. And once you find 0, the previous remainder that you find is called greatest common divisor. Okay? No computer usage or laptops or these. Okay. So greatest common divisor of these two is 4. This is what we have. And the question last time I asked for sort of challenge was why this is true, why does it work? So why the greatest common divisor comes up from constantly dividing these numbers to each other. So anybody had a chance to think about this? Maybe tell us some things. It's a long proof. Is it like from the book? Okay, so maybe I will summarize it or give you the basic idea. The reason this division algorithm works is basically observing that the greatest common divisor of these two numbers is same as greatest common divisor of these two numbers. So each time we have a division, we'll see that the greatest common divisors doesn't change between these numbers and these numbers. Okay? So the idea is the reason Euclid's algorithm works is that greatest common divisor of these numbers 5, 4, 4, 8, 4, same as greatest common divisor of these two numbers, 84 and 40. And it's same process. Whenever you have a division here, the greatest common divisors carries to 40 and 4, and then same thing, 4 and 0. But whenever you're looking at greatest common divisor, two numbers, 0 and 4, that's always the non-zero number. That's the greatest common divisor. Everything divides 0, so the greatest thing that divides 4 is 4. So because whenever you reach 0, the other number becomes your greatest common divisor. That's why it stops there with 0, and the previous number becomes your greatest common divisor. So it's again an induction process, because once you know this, you also know this, you also know this. So what we know here is something you can state.
It sounds like it's the algorithm itself.
Yeah, I mean, you actually induct the process of using this idea that if you divide this to this, if you get remainder r, greatest common divisor is same between this and remainder. I will write this now statement. So this follows from this statement that we will have to verify. If we divide n to m, positive integers, with, say, n is bigger than m, we get unique numbers. This is called division rule, right? We get unique numbers, q and r, such that n is equal to Actually, I used A and B. Let's go back to A-B statement. A is equal to BQ plus R with R positive and less than B, strictly less than B. So this is called division, right? Division algorithm. That's division rule. The statement we have says for positive integers A and B with A plus B and A is equal to BQ plus R, we have, so this statement says greatest common divisor of A and B, greatest common divisor of A and B, yanlış.
Their linear combinations.
Huh?
Their linear combinations.
Line is equal to your huh?
R and B.
R and B. Greatest common divisor of the other two. Yes. I thought you were correcting a mistake. That's why I hesitated. So this is the statement. Anytime you divide A to B and you get quotient Q and remainder R, the greatest common divisor of A and B is same as greatest common divisor of B and R. That's the statement. So if I can verify this by pure arguments, division algorithm and numbers, then I will know that this division algorithm works. Because this is exactly what we use here. This is B, this is R. And then I repeat it again. But the repetition is just using the same statement again and again. So it's an inductive process. So all I need to verify is this statement.
Do we have to prove that if there's a unique, not unique, there's an integer divides A and B, also divides R? And
we will verify things like that anyway. But we have to verify the statement by using basic arguments about division. Yeah. So let's try to verify this statement. I mean, many of you will think it's actually obvious because you can see that if something divides A and B, it will divide R, so it will divide B and R. In the other direction, things dividing B and R will divide A, so it will divide A and B. So there is some correspondence between things that divides both A and B and R. Because of this correspondence, the greatest of these common divisors should be equal. You can argue like that. This is actually as good as a proof I'm going to write. But the argument comes from the fact that you can write this equation. Anytime you have a division, that's the equation you have. So first, let's review what greatest common divisor is. First of all, technically in number theory, it's defined as not the biggest number, but it's the number where all the common divisors divide. So it's actually equivalent definition, but you have to state it that way to make it more workable with division. Okay, so given positive integers A and B, we say C is common divisor if C divides A and C divides B. So remember, this is the notation to say C divides A and C divides B. So a positive integer D is called a greatest common divisor. Common divisor if first it should be a common divisor. Second, It should be the greatest, but not only numerically, but also in the division relation. So that means any other common divisor should divide D. If C is a common divisor, then C divides D. So it's not only like order relation greatest, but it's greatest in the common divisor sense. To just make it a little bit more, let's say we are dealing with 24, 3s and 8s, and B 36. So divisors of this, there are 2s and 3s and so on. So you can actually factor this out, 2, 2, 2, 3. You can write these factors also, 2, 3, 2, 3. So you can see that common divisors are 2, 3. So common divisors. 1 is always a common divisor of all integers. You have 2 as a common divisor, 3 is a common divisor. Is 4 a common divisor? 4 is a common divisor. 6 is a common divisor. 12 is a common divisor. 8 is not a common divisor. 8 does not divide 36. So these are the common divisors. And the greatest common divisor is the biggest number, but also it is the one that all the other common divisors divide. So here, the greatest common divisor is 12. Okay? So it's not only the greatest number, but also all the other common divisors divide it. You can easily prove it by that these two definitions equal, but I will not do that. So this is going to be our definition from now on. So we'll think that common divisor is the one that all the other divisors, all the other common divisors divide. So greatest common divisor is the one that all the other divisors divide. All the other common divisors divide. So with this information, now it's easier to look at this. Now I'm looking at, say, greatest common divisor on this side and greatest common divisor on this side. They're both greatest common divisors, and I need to show they're equal. So I think today's lecture will be devoted to proof of that statement. So let me show how to prove that statement. So I want to show these two things are equal. One of them is the greatest common divisor of A and B. The other one is greatest common divisor of B and R. And I know this equality. Just to remind you, like if a number divides other one, if like D divides A, then this means that A is like D times K for some integer K. Since we always work with positives in this proof, it's actually a positive integer. But divide means that you can find another integer. When you multiply the lower one, you get this one. That's the definition, right? So we're not dealing with real numbers. So we in real number sense, everything is written as, like you can always take K, A over D. But in real numbers, you can do it. But in integers, you cannot find the integer, right? Like 3 does not divide 2. You don't have an integer to make it. So you're not allowed to put 3 over 2, of course. That's why it's integer. Okay? So it's number theory otherwise. So what's the good way to prove that they're equal? Can we come up with some clever idea that will give us that they're equal? What's a good way to show two integers are equal?
We can write instead of A, B times K. k square?
B is not divided by R, divided by D1.
No, no.
Mm-hmm.
We are looking for this common divisor, and I assume that it is k.
Okay. Let's say D1 and D2. I already introduced them, right? So you're saying that D1 is the greatest common divisor of A and B, so that means D1 divides A. That's what you're saying. So that means I can write A as K times D1, or D1 times K. We can do this for B as well. So B is equal to K times D1. Let's use another letter, L times D1.
K, instead of k, we can write b, right?
Instead of K, no. B does not divide A. It only D1 divides A. But you're in a good path. So I wrote A and B multiples of D1. What can I get out of this? To answer. Yes.
We can multiply B with Q and subtract to show that R divides.
So you can check this equality. Right? We can put these into that equality. K D1, L D1 Q, and get this.
Then R should divide.
So you can say that R is equal to K D1 minus L D1 Q. Factor out the D1. So D1 divides R. Is it? So we show that if D1 is the greatest common divisor of A and B, it has to divide R. Mm-hmm.
For us to prove that these two numbers are equal, we need to show that D1 divides D2 and D2 divides D1.
So that's what I was trying to get. So the idea that we want to do, is we want to show D1 divides D2 and D2 divides D1. So if you have two positive integers, these are all positive integers. If one divides the other one, and then the other one divides the first one, they have to be equal. There are no two integers which divide each other without being equal. Two positive integers. You can actually verify this by using this idea. Let me actually write a small note about it. I'll come back to it, but this is what our aim is. We want to show that they divide each other. If they divide each other, they will have to be equal.
Can apply the same procedure to B and R?
Okay, so let me write this. So if D1 divides D2, that means D2 is equal to some m times D1. If D2 divides D1, that means D1 is equal to some n times D2. Combine these two, you get this. But then you get D1, 1 minus nm is equal to 0. This is positive integer. The only way you get 0 is this product is 1. You have two positive integers whose product is 1. It's only possible if they're both equal to 1. Right? That's because any other integer is bigger than 1. If you multiply them, you get something bigger. You cannot get 1. Okay. So that's why this is an idea that works. Okay. So now going back to what you said. I already argued that if D1 is the greatest common divisor of the first thing, A and B, then it divides R and it divides B. So what can I get from this? Let's try to see. If I can get D1 divides D2. Can I get d1 divides d2? Why can I get that?
If the greatest common divisor is
Uh-huh.
D2 and D1 is
Uh-huh.
dividing both of them.
So d2 is the greatest common divisor of b and r, right? And these two are common divisors. So the conclusion should be that a common divisor should divide the greatest common divisor. So d1 should divide d2. It's the definition. I will show you in a few seconds. So it's the definition of greatest common divisor is that it should be divided by all the common divisors. Greatest common divisor is the one which is a common divisor, but also divided by all the common divisors. So that means the greatest common divisor of b and r, which is d2, should be divided by d1 because d1 divides both of them. Okay? So I obtain this statement that d1 divides d2. I need them, they both divide each other. So I need the other one. How can I get the other one?
You can go in reverse order.
We can repeat the process. So start with d2 this time. This is greatest common divisor b and r. So it divides b and it divides r. But a is equal to bq plus r. So if you have something that divides both of them, that means you can actually write b as d2 times some k. Let's use other letters, z. And then you can write r as d2 times some other letter, t. Same way we did before, you can factor this like this. So you find that d2 divides a. And what we do with d2 divides a?
D2 divides A, D2 divides
d2 divides b, d2 divides the greatest common divisor, which is d1. So I found d1 divides d2 here. I found d1 divides d2. Here I found d2 divides d1. There are no two integers that divide each other unless they are equal, two positive integers. So I conclusion is that these two are equal. They have to be. I mean, if they were integers, we can allow plus minus, but they're both positive integers. They have to be equal. They can't divide each other unless they're equal. It looks like it's just tricks. You put it there, you put it there, obvious things, but at the end you get something very powerful. At the end you see that everything led us this calculation. At the end you get very applicable thing that you found an inductive process of reducing greatest common divisors to just calculating some divisions. That's what we got. Let me see, I have time. Okay, I have 3 minutes. We can take one more question if you have a question. Okay, all for today. So we'll meet Friday, usually, 2 hours lecture.